Okay, so today we're going to continue with specific heat capacity. Okay, but today we're going to look at the essay question. Essay question. So okay, so we look at question number 29. So diagram 9.1 shows two identical electric kettles P and Q are filled with different quantity of water. So diagram 9.2 shows only kettle P releasing steam after 5 minutes of heating. Okay. Okay, so the first thing is what is the meaning of heat? So they start with definition. So heat, you can say, is a form of energy. Okay, it's a form of energy. Okay, next. Using diagram 9.9, 9.2, compare the mass. Okay, so you're supposed to compare the mass, compare the heat supplied, and compare the rise in temperature. Okay, so compare the mass, compare the heat supplied, compare the rise in temperature. So these 3 marks. Okay, so these 3 marks, right? So now what we can say about the mass? So the mass, you can see here, right? So diagram 9.1 greater than diagram 9.2 lah. Okay, so mass of water in diagram 9.1 greater than diagram 9.2. 9.2 greater than 9.1. Okay. Okay, next we are talking about heat supply. So if you see, right, heat supply. Okay, so what happened is your kettle is the identical kettle. Okay, so the identical kettle. That means the heat supplied is the same. Okay, so heat supplied, okay, is same. Okay, because they have the same power. They have same power. So heat supplied will be the same. Okay, then the rise in temperature, we can see this one faster than this one, because this one, after 5 minutes, you can see the steam. So rise in temperature, okay. Okay, diagram 9.1 greater than diagram 9.2. Okay, so rise in temperature, diagram 9.1 greater than 9.2. So all these you get 3 marks lah. And then they ask you to change between mass and the rise of temperature. So you can say the smaller the mass, the greater the greater the rise in temperature. Okay, so the smaller the mass, the greater the rise in temperature. Okay, now so state the physical quantity that must be constant to deduce relationship between the mass and rise in temperature. Okay, so the physical quantity. Okay, now so this one basically, right, from the formula. Okay, Q equals to MC theta. Okay, so Q over MC equals to theta. Okay, so what we have here, right, the smaller the mass, the greater the rise in temperature. So this situation is talking about mass and rise in temperature. So what we have here is the Q and the C, right, must be constant. Okay, so both the heat supplied and the specific heat capacity must be constant. So the Q and C must be constant. Okay, then only we can say when the mass decrease, the change in temperature increase, or when the mass increase, change in temperature decrease. Okay, so that means physical quantity that must be constant So here you can say, okay, heat supply, okay, or specific heat capacity. Okay, so heat supply or specific heat capacity. So these two must be kept constant. Okay. Now next we look at C. Now lemonade can be cooled by adding ice cubes into it. Give an explanation based on the above statement. So lemonade can be cooled by adding ice cubes. Okay, 4 marks. Okay, 4 marks. That means you might have 4 points. So first you can say, okay, when ice cube is added into into lemonade, there will be thermal contact. Okay, so the keyword here, thermal contact. That means there must be thermal contact, okay, in order for heat to be transferred. So there'll be thermal contact between the lemonade and the ice lah. Okay, so when ice added lemonade, there'll be thermal contact between the ice and lemonade. Okay, and then next you say, okay, temperature of lemonade, okay, is higher than ice. Okay, so temperature of lemonade is higher than ice. Next you say there is net flow of heat from lemonade to ice. Okay, okay, so there's net flow of heat from lemonade to ice lah. So this one will melt the ice. This one will melt the ice. So later in the next chapter you will look at latent heat. Okay, so latent heat of fusion. So this one actually is latent heat of fusion lah. Okay, so so the heat from the lemonade will be transferred to ice, causing the ice to melt lah. Okay, ice will melt. Okay, so that means the heat as well we call it as latent heat. Okay, but this one we look more when we look at the next subtopic. Okay, latent heat. Okay, so there's net flow of heat from lemonade to ice. Okay, so this causes the temperature of lemonade to drop. Okay, so this causes temperature of lemonade to drop. That means the lemonade will cool down. Okay, or this causes temperature of lemonade to decrease. Okay. Okay, next D. Now diagram 9.3 shows a lidded cup. The cup is not suitable to be maintained the temperature of hot drink for a long time. So it required to suggest a suitable characteristic of the lidded cup in diagram 9.3 that can maintain the temperature of hot drink for a long time. So your state and explain your suggestion based on the characteristic of the material of the cup. Okay, and the lid. So characteristic of material of the cup and the lid, and then the method of keeping the drink hot. Okay, the method of keeping the drink hot. Okay, so this one actually you can answer in the form of table. Okay, so you can answer in the form of table. Okay, so characteristic of material of the cup and the lid and the method lah. So they give you 10 marks. So when they give you 10 marks, you must have 5 modification. Okay, you must have 5 modification. So for this one, so you can put into 2 columns. So this column is say as modification, and then here we can say reason. Okay. Okay, now they want characteristic of the material of the cup in the lid lah. Okay, so you can say, okay, material of cup Okay, cup and lid must have high specific heat capacity. Okay, must have high specific heat capacity. Okay, so this one actually from the formula, right? Q equals to MC theta. So Q over MC equals to theta. Okay, so higher specific heat capacity, that means smaller changes in temperature. That means doesn't become hot easily lah. So you can say does not become hot easily. Okay, next. Okay, so still under the characteristic of the material of the cup. Okay, so they say characteristic, right, of the material. So you don't need to name the material, So you just say what are the characteristics you want. Okay, so you can say the material of cup or indeed, right, must be poor conductor of heat. Okay, so you can say does not absorb. You can say poor lah, poor absorber of heat. Okay, poor absorber of heat. Okay, next. Okay, so we can talk about, okay, what is that, in terms of how to keep the water cool for a long time, right? So you can talk about the color, okay. So the cup and lid must be bright, okay, bright color. So reason, good reflector of heat. Okay, good reflector of heat. Okay, must be bright in color lah. Okay, good reflector of heat. And then, okay, can say the lid must be airtight. Okay, so to reduce heat loss through convection. Okay. Now we know that heat can be lost in three methods, right? Conduction, convection, and radiation. So let's say if this is your cup, right? Okay. So let's say what happened is, okay, inside here there is hot water. Okay, so the hot water. So meaning what happened? The air inside there also will be hot now. Okay, so the air trap inside there will be hot. So if it's not airtight, what happened? The cool air can come. Okay, can come in, and then what happened is the heat from the hot water is transferred to the hot water, right? So the heat from the hot water is transferred to the air, then the air goes out. So this one we call it as convection, convection. So heat loss through convection. So that means there'll be a flow of air here. Okay, so the air comes in, take the heat and goes out, and then cools out, and then go in and take the heat and goes out. So this one causes the hot water to cool down. Okay, so that's why it must be airtight. Okay, and then it must be bright in color so that, okay, the heat can be reflected back into the cup. Okay, so inside and outside must be bright in color so that the heat can be reflected back into the cup. Okay, and then usually, right, you see that the cup, okay, will have two layers. Okay, so the cup will have two layers. So what we do is between the two layers we have a vacuum. So between this layer we put a vacuum. So 2 layers separated by vacuum, because vacuum can prevent heat loss through conduction. Okay, heat loss, conduction and convection can be reduced using vacuum. Okay, radiation cannot lah. Okay, it can be radiated out, but to conduction, convection, we can prevent using vacuum. Okay, because if there is air, so this air, what happen? It can causes the heat to be lost through conduction and convection. Okay, so if you put a 2-layer vacuumer, that means the heat cannot be transferred out through conduction and convection. So that means the cup must have 2 layers. Okay, so another way you can say, okay, so cup has 2 layers separated by vacuum. Okay, so this one you can say to prevent heat loss through conduction and convection. Okay, this one you can prevent lah. Okay, something we cannot prevent the heat loss. We can reduce lah. We can slower. Okay, we can slower the heat loss. Okay, but vacuum can lah. But end of the day, you see that after some time also the water will cool down lah. Because even though it's vacuum, the heat can be lost through conduction. And also, the heat can be lost through radiation also. Okay, can be lost through radiation. Okay, so even though you don't open, it can still be lost through radiation. So the temperature will go down lah, but it will take a longer time. Okay, it will take a longer time. Okay, so these are example of the answers lah that you can give. Okay, these are example. Okay, so basically you must have 5 modification and 5 reason. Okay, 5 modification, 5 reason. Okay. Okay, now we look at another example of question. Okay, this one. Now diagram 9.1, 9.2 shows 2 identical frying pan filled with cooking oil of different amount used to fry identical fish on a gas stove. The cooking oil has a low specific capacity. So after a few minutes, it's observed that the fish in diagram 9.1 is scorched, and the fish in diagram 9.2 is well cooked, even though they was fried under the same state of flame. So what is the meaning of specific heat capacity? So basically heat needed. So this one you can refer to your notes, the earlier one. So heat required to change temperature 1 kilogram substance by 1 degree Celsius. Okay, so this is a specific heat capacity definition. Okay, next. Now using diagram 9.1, 9.2, compare the mass of the cooking oil. So compare the mass. So mass, you can see this one is lower than this, right? So mass of cooking oil, you can see diagram 9.1 lesser than diagram 9.2. Okay. Next, the quantity of heat supplied. So the flame is same. So you can say same lah. Same. And then the final temperature. So this one is more than this lah. That's why this one the fish got burnt. Okay. So diagram 9.1 greater than diagram 9.2. Okay. Next. Relate the mass of the cooking oil with the state of the fishes to deduce relationship between mass and increase in temperature lah. Okay, so this one actually is same like just now. So the lower, right, the mass of cooking oil. Okay, so the more. Okay, so they use the word here scorch, right, or burnt lah. The more scorch the fish. Okay, so the lower the mass of cooking oil, the more the scorch is. Okay, relationship between mass and increase in temperature. So the lower the mass, the higher the increase in temperature. Okay, next, they ask you to explain how sea breeze phenomenon occurs. So this one you're given 4 marks. Okay, 4 marks. Huh? So how sea breeze occurs. Huh? Okay, this one happen during daytime. Huh? So you can say, okay, so during daytime, right? Land is hotter than sea due to lower specific heat capacity. Okay, due to lower specific heat capacity. Okay, next. So the air above the land is hotter and has lower density. Okay, compare the air above the sea. Okay, so air above land rises up. Okay, creating area of low pressure. Okay, so the meaning, right? What happened? So the air is hot here, right? So the air will be having low density. So that means the air will be lighter. So the air goes up. Okay, so the air goes up. So when the air goes up, that means this area becomes something like semi-vacuum lah. Okay, it becomes something like semi-vacuum. Huh? So this area becomes semi-vacuum because it's empty. The air has gone up. So semi-vacuum. So what happened? This area will have low pressure. Okay, okay, area of, you can say semi-vacuum lah. Okay, semi-vacuum. Okay, or low pressure. Huh? Okay, low pressure lah. Okay, so this causes wind to blow from sea to land. Okay, so this causes wind to blow from sea to land. Okay, so you get 4 points. 1, 2, 3, 4. Okay, salah. Okay, huh? Now, next we look at the question here, right? Now, diagram 9.4 shows a car engine radiator. So you are required to design a car engine radiator which can function effectively based on the following aspect. So the size of that fan, the number of fin blade, material of the fin blade, specific capacity of the coolant liquid, and the boiling point. Okay, so now, so same thing. This one you must write modification and reason. Okay, okay. So size of fan, you say okay, big. Okay, reason can suck in more air. Okay, can suck in more air. Okay, and then the number of fin blade must be many. Okay, okay. Now, what is the function of the fin blade? Now, you see that what happened is, okay, let's say the liquid, right, the water lah, the water will be pumped. Okay, so the water will be pumped, so it passes through closest to the engine block. So the heat from the engine will be transferred to the water. Okay, so the water become hot, and then the water will be pumped back into the radiator tank. Okay, so now this water is hot water. Okay, because I've absorbed heat from the engine. So what happened? The hot water, okay, this is a fan. So what happened? The fan will suck in air. So there'll be air coming in. So what happened? The heat from the hot water will be transferred to the air outside. So the air cools down. Okay, now the idea of the fin blade basically is to increase the area, okay, because without the fin blade, okay, the heat will be transferred by at the surface of the what do you call it, surface of the radiator. But if you put fin blade, it's like a metal piece, so it's like a metal piece here. So it's a fin blade, metal piece. So what happens? You increase the area for the heat to be transferred out. So now the heat can be transferred out to this metal, okay, to the fin here. So the fin plate is just a metal, okay, so so that means you increase the area for the heat to be transferred out. That means the water can cool down faster, okay. So this one you can say, okay, increase the area, okay, for heat to be transferred out. Transferred out from water. So basically to cool down the water faster lah. Okay, so if you say want to cool down the water faster also can. Okay, so material of the fin blade, right? So this material must be, okay, so this material of the fin blade, right? So the material of the fin blade, okay, you can name the material is copper. It's copper because it's good conductor of heat. Copper is a good conductor of heat. Okay, okay, good conductor of heat. If you put metal, right? Metal is too general lah. Sometimes if you put iron, you're not suitable because iron will rust. Okay, so you can put copper lah. Good conductor of heat. Okay, so good conductor of heat. Okay, specific heat capacity of the liquid used. So from the formula, Q equals to MC theta. Okay, so Q over MC equals to theta. So we want the liquid to have high specific heat capacity so that the liquid doesn't become hot easily. Okay, so we want the liquid, right, after absorbing the heat from the engine, doesn't become hot easily lah. So specific capacity of the liquid used, you can say high. Okay, reason does not become hot easily. Okay, and then boiling point of the liquid, boiling point must be high. Okay, so reason does not change to gas easily. Okay, does not change to gas easily. Okay, because why? If the liquid change to gas, okay, if the liquid change to gas, what happened? The volume of the liquid inside it will start to reduce. Okay, the volume will start to reduce. Okay, okay, will start to reduce. Okay, okay, so the volume start to reduce. So what happened is, okay, then it's not enough to absorb the heat from the engine. Okay, so okay. Now another example of this question. Modification, right? Now diagram below shows a simple solar water heating system. Energy from the sun falls onto the solar panel. Water is pumped around the system so that a store of hot water is made available in the tank. So using suitable physics concept, explain the required modification needed designing an efficient solar water heating system. The modification should include the following aspect lah. So the pipe design, the pipe design. Okay, now you see what happened is this is your solar panel. Okay, now let's say if this is your pipe. Okay, so this is your solar panel. Okay, solar panel. So this will be the pipe. So what happened is, so let's say the heat come from the sun and then, okay, received by the solar panel. So the solar panel, what happened? Get heated up. So what happened? The pipe in contact with the solar panel, the pipe also get heated up. So the water inside the pipe also get heated up. So if the water get heated up, now you see what happened is, the area of contact between the pipe and the solar panel is only this much. Okay, so it's quite short. So usually what we do is, we make the pipe into a coil shape. Okay, so we make the pipe into coil shape. That means to increase the area of contact with the solar panel. Okay, that means more area of contact solar panel lah. So pipe design here you see it's already in coil shape. We say more coil lah. Okay, so more coil. Okay, so reason increase area of contact with the solar panel. Okay, increase area of contact with solar panel. Okay, so this one is the pipe design, right? Okay, this is the pipe design. Okay, now material used for the pipe. Okay, same thing lah. Huh? So material you can say copper. So reason good conductor of heat. Okay, conductor of heat. Okay, next. Heat absorption. Heat absorption. Okay, so heat absorption, that means we want to increase the heat absorption. Okay, so heat absorption, you can say the pipe, right? You can talk about the color of pipe. So pipe, dark in color. Okay, so reason good absorber of heat. Okay, so the pipe must be dark in color so that it good absorber of heat. Okay, now other than that, okay, heat, you see, you want okay, the heat to be absorbed faster, right? So the heat to be absorbed faster, you can even see, right? Okay, pipe, right? Must have low specific heat capacity. Okay, reason become hot faster. Okay, so become hot faster lah. Okay, so the modification low specific capacity, reason become hot faster. Okay, and then the position of the tank. Okay, so position of tank you say high. Okay, so that water can be supplied at high pressure. Okay, so that means the water will come out faster lah. Okay, so water will be supplied with higher pressure. Okay. Okay, another example. Now, diagram 8.1 shows the design of a solar cooker. So the cooker heats the water using infrared radiation from the sun. So some modification need to be done on the curved dish and the cooking pot so that the water can boil faster. Suggest the modification based on the spec. Okay, size of the curved dish. Okay, so what happened? This is a concave reflector. So we know that when the light ray come, it will be focused. Okay, so the light ray will be focused. Okay, so all the light ray will be focused. Okay, so meaning what happened is we want to have size of the curved dish must be big. Okay, so reason can reflect, okay, or collect, okay, more light ray. Okay, can reflect or collect more light ray. Okay, next, type of inner surface, right? So we want the inner surface to reflect. Okay, so type of inner surface, you can say, okay, the inner surface must be shiny. Okay, so good reflector of heat. Heat can, light also can. Good reflector of heat, good reflector of light. Because the light will produce, the light will supply the heat. Okay. Okay. So position of the pot. So this point, right? Okay, this one we call it the focus point. Okay, so this will be your focus point. So that means all the energy is focused at this point. Okay, so all the energy is focused at this point. That means you get the maximum heat here. Okay, so you get maximum heat. So position of the pot, you can say at the focal point. Focus point. So reason to get maximum heat. Okay, so to get maximum heat. Okay, material of the pot. So we want the pot to have can get heated up, right? So material, if you want to put copper also can, if we say low specific heat capacity also can, so it become hot faster. Okay, become hot faster. Okay, now color of the pot. This one you want to have a good absorber of it, so color must be dark. Okay, so reason good absorber of heat. Okay, so this is a sample. Okay, answers that you can give. Okay, now, so we look at another example. Now, this one will be another style of your essay question. Now, diagram 11.1 shows clinical thermometer used by a doctor to check the temperature of patients' body during medical treatment. So, what is meant by temperature? So, temperature is degree of hotness. Okay, degree of hotness. Now, referring to the principle of thermal equilibrium and working with thermometer, explain how a doctor can check his patient's temperature during medical treatment. Okay, so this one, 4 marks, right? So first you can say thermometer is under arm, okay, to produce thermal contact. Okay, so thermometer placed under the tongue to produce thermal contact. Next. Okay, so there is temperature of person greater than thermometer. So there is net flow of heat from person to thermometer. Okay, so what happens is from person to thermometer until thermal equilibrium is achieved. Okay, achieved lah. Okay, so then say temperature of thermometer equal to temperature of person. Okay, so you get 4 marks for all this. Okay, now next. Okay, this one for this essay question. This is another style of essay question. Okay, there's only 2 styles of essay question for paper 2. Okay, this for section C. The earlier one you did is section B. This is section C. Okay, section C will have a bit of calculation. Okay, a bit of calculation. So if you look at diagram 11.2 shows a thermometer which is not calibrated. A mercury column of length 5 cm when the temperature is 0 and 25 cm when the temperature is 100. The mercury column LO is 12 cm and placed in liquid X. So name the physical quantity changes when the mercury, when the temperature changes. So the physical quantity changes here, you can say volume, okay, or the length. Okay, volume or length. Okay, now determine the temperature of liquid X. Okay, so determine the temperature of liquid X. Okay, So this one, right, you can use the formula lah. This one is from the previous subtopic. Okay, so theta, right, equals to L theta minus L0 over L100 minus L0. And then you have to times with 100 degrees Celsius. Okay, so your L theta is 12. So 12 minus 5 over 25 minus 5 times 100. Okay. So 12 minus 5 divided with 20 times 100. 35 degrees Celsius. Okay, next, what is the length of mercury column from the bulb of the temperature 30? So this one you want to find your L theta. Okay, so this one you want to find your L theta. So that means use the same formula lah. So that means 30 degrees Celsius equals to L theta. Okay, so your L0 is 5 over 25 minus 5. Okay, so times 100 degrees Celsius. Okay, so 25 minus 5 is 20. So this 20 and 100 you can cancel, so you get 5. Okay, so actually what you're getting here is you get like this. So 30 degrees Celsius, 30 lah. So 30 equals to L theta minus 5 times 5. Okay, because 20 you cancel with 100 already. So this 5 actually you can bring down, cross multiply, bring down. So it becomes 30 over 5. Okay, 30 over 5 lah. So it becomes divide. So 30 over 5. So it becomes 6. So 6 equals to L theta minus 5. So you can find your L theta lah. So L theta will be 11 cm. Okay, 11 cm. Okay. Okay, next. Diagram 11.3 shows cross-section shape and the characteristic of material for 4 rice container JKLM, which are used to maintain the temperature of hot ice. You are required to determine the most suitable rice keeper. Okay, that means container to keep the rice hot for a long time. So study characteristic and choose the most suitable. Choose the most suitable. Okay, so basically you need to choose the most suitable container to keep rice lah. Okay, so this one, your what you can do is, okay, your answer, right? You write in the form of table. Okay, but for this, right, the first column here will be characteristic. Okay, characteristics. So this column will be your reason. Okay, reason. Okay, so melting point. So melting point. So they got put the value 240, 240. Right? So you don't write the value. You say whether you want high or low. So melting point, you say high. Okay, must be high. Okay, so reason does not melt easily. Okay, and heat it up. Okay, so doesn't melt easily. That means doesn't change liquid easily. Okay, next, specific heat capacity. So specific capacity, right? For the this one, right? Container. So specific capacity must be high. Okay. So reason does not become hot easily. Okay. Because if become hot easily, that means you cannot hold the container. Okay. And then the density, right? Okay. Density also same. Do not write the number. Huh? Do not write the number. Density just say low. Okay. So density must be low lah. So reason tighter. Okay, and then material between the inner wall and outer wall. So material, there's a polystyrene, there's a copper. So we want the heat to be transferred out at a slower rate. So we use a polystyrene lah. Okay, we use a polystyrene. Okay, so this one, right? So material between the inner wall and outer wall. Okay, so polystyrene. Okay, polystyrene. TY. Okay, polystyrene. So because wood insulator of heat. I can say poor conductor of heat also can. Okay, it's up to you lah. Okay, it's up to you. Okay, now after you choose all these, you have to choose the best model here lah. Okay, so I think the best model will be here. Okay, this one, right? The best model will be K. So and then after that, the last one, okay, so what do you do? This one bottom may become conclusion lah. So K is most suitable because, okay, so you have to repeat all the characteristic back. So you have to repeat all this back. Okay, so the melting point is high, specific capacity is high. Okay, the material is polystyrene and so on. Okay, so you need to repeat the characteristic. No need to repeat the reason. Okay, so repeat all the characteristic. No need to repeat the reason. Okay. Okay, okay, now we look at one more example, F. Now diagram 11.1 shows the thermos flask used to maintain the temperature for drink for a long time. So table 11.1 shows the characteristic of 4 different thermo flasks. So explain the suitability of each characteristic of thermos flask and determine the most suitable one. Okay, so this one also same. You give your answer in the form of table. Okay. So the first column here, you have characteristic. Okay, and then this one will be your reason. Okay, so so here characteristic. Okay, the stopper, is it hollow plastic or solid plastic? Now hollow plastic, that means what happens is this area inside there is hollow. Okay, now what we want is we want the stopper, right, to make the opening here airtight. That means we don't want the air to go in or the air to come out. Okay, so we try to make it what they call it airtight. Now, if the plastic is hollow, that means easy for you to squeeze. That means the stopper can be bigger size than the opening, so it can squeeze easily because this area inside there is hollow, right? So that means you can squeeze it to make it smaller. Okay, so make it smaller. Then when you put inside here, it will expand. It will expand a bit, so you make it airtight. Okay, can be make it airtight lah. Okay, so you can say okay, the stopper, right? So you can say stopper. Okay, stopper must be hollow plastic. Okay, hollow plastic lah. Okay, so that okay, the opening, right? Be airtight. Okay, okay, can be airtight. Okay, or you can even say that because when it's hollow, right, inside there will be air. Okay, so that means air here become poor conductor of heat. Okay, air is a poor conductor of heat lah. Okay, so air poor conductor of heat. Okay, or another way is, because if this thing is hollow, let's say inside there is vacuum. Okay, let's say inside there is vacuum, so that means we can reduce the heat loss through conduction also, because inside here there is less air. I say less atom. Okay, there's less atom, so it taken out, so it becomes hollow. Okay, so it become hollow. Let's say if this vacuum, that's more better lah. So we can reduce the heat loss through what do you call it, conduction. Okay, or you can even say reduce heat loss through conduction. Okay, because right, if it is not hollow, that means you have atoms, all this. Okay, so there'll be atoms here. Okay, so there'll be atoms, so the heat can be transferred out, can be transferred to the atom, can be transferred out. Okay, the heat can be transferred to conduction. So that means the heat can be transferred to this atom, and this atom. If it is hollow, let's say if it is vacuum, so that means the heat to be transferred out is much more difficult lah, unless through the side. To the side transfer here, to transfer, so it will be slower lah. Okay, reduce heat loss through conduction. Okay, now space between here, right? The two space here lah. So the space P must be vacuum. Okay, vacuum. So space P must be vacuum. So reason you can say, this one you can say lah, prevent loss through conduction. Okay, and convection. Okay, so can prevent heat loss through conduction and convection lah. Okay, now the glass wall tube, here, the inside here, right? So the inside here we want to be a poor conductor of heat. So the glass wall tube, okay, made of glass. Okay, okay. So the double wall tube, right? The double wall tube made of glass. Okay, so double wall tube made of glass. Okay, so reason can say poor conductor of heat. Okay, and then finally, right? Okay, coated by, so we want the heat to be reflected back. So we want the heat to be reflected back. We want the heat to be reflected back. So coated by shiny paint. Okay, so coated by shiny paint. So reason, good reflector of heat. Okay, good reflector of heat. Okay, so the double wall tube made of glass, double wall tube coated with shiny paint, because good reflector of heat. So after you write this, then only you have your conclusion lah. Okay, so which is the best? Okay, correct. So W is most suitable. Okay, because okay, you can repeat back all this lah. Okay, because why? Because the stopper is hollow plastic, and then the space P is vacuum. Okay, made of glass, the double wall, and then the double wall is shiny paint. Okay, so W, then you have to repeat back the characteristic. Okay, so repeat back the characteristic. Okay, so no need to repeat back the reason, repeat back the characteristic. Okay, so this is how you answer, okay, your paper 2 essay question. Okay, so this example of question, okay, for heat. Okay, so that's all for today. Okay, so we'll continue on the next lesson.